All right. So, hello to Rachel and Marty. And is that it? Is that what we're missing today? Oh, Parker, right? He's so loud. It's hard to know he's not here. All right, great. Here we go. Parent functions. Today we're going to talk about some different shapes that you guys should know. This one will be linear. So y is equal to, say, 3. That's a horizontal line passes through 3. I would expect that everybody knows that that's a horizontal line passes through 3. We good to go? Okay, then here's another linear function. Y is equal to x. That has a slope of 1 and passes through 0. Are you able to commit those to memory? Good, because you need to commit everything on this page to memory. Y is equal to, let's do the absolute value of x. Oh, it's very similar to y equals x. It's just got this crazy absolute value sign on it. Well, if it's got absolute value, what does absolute value do? Makes it positive. Well, so this portion that's negative will become positive. So therefore, it looks like this. It's not like these are just made up out of thin air. The fact is that these shapes represent the algebraic structure, and it does what we tell it to. We're not going to do the greatest integer function or the least integer function or floor functions or ceiling functions. They're just not that important. But we will do a power function, such as y is equal to x squared. What does that look like? Parabola, great. I know you can commit that to memory because you've already known that's a parabola for a while. Let's quickly think about why it gives it the shape that it does. If you square a real number, it's going to be positive times a positive is a negative times a negative is a positive. So if you square a real number, it will always be positive. That's why it always sits above the x-axis. Are you convinced? What if we cube something? If you cube a positive, you get a positive. If you cube a negative, you get a ooh. So it looks like if you cube a negative, it will produce negative results. So therefore, negative x values have negative y values. Positive x values will produce positive y values. Hi. What can I do for you? Y equals x to the fourth. Do you think it'll look more like y equals x squared or like y equals x to the third? Why? Yeah, because it will always produce positive values. Now, the fact is that it looks very similar, but it has a little bit more of a U shape to it. And for this, I'm going to go to my calculator, and we're going to have a little bit of fun. I know you're like, well, Mr. Gens, everything's always fun in math. But we're going to look at something that is kind of especially fun. I'm going to look at x squared, and then x to the fourth, and we'll check out even x to the eighth. And I'm going to create a window here for you. I'm going to go negative, let's go 2 to 2. I'm going to go negative 1 to 4. And you tell me what's happening each time with these shapes. That's x squared. That's x to the fourth. Yeah, see that? Kind of neat, huh? What if we increased it to a very large positive integer that's even? Somebody want to give me an example here? X to what power? 216? You just went to 216. Oh boy, did you know that's a perfect cube? 6 times 6 times 6. Good job. 666. Whoa. Yeah. Kind of cool, huh? Yeah, it looks like a beaker. Very good. And it looks like it actually has a corner on it. It turns out that it will never achieve a perfect corner. It will always be a little bit rounded, but it will always be a sharper corner as we move forward. So kind of interesting how that works. Y equals x to the fifth. Well, that's going to look a lot more like y equals x to the third. Just going to flatten out around 0 as well. So that's kind of what happens to those. If I asked you on the test to draw a curve of x squared or x to the fourth, I'm not going to ask you to show the difference between them. Just the general shape is fine, okay? So let's look at root functions, like y equals the square root of x. Now, we just spent some time talking about the domain of the square root of x. And that means the values you can plug in for x. What can't you plug in for x? Can't plug in negatives. Why? Can't take the square root of negative numbers, could produce an imaginary result. So therefore, we just have positives. Hi, I'm popular today, huh? Awesome. What do we got here? All right. Doyle. Man, you're popular. Cassandra. There you go. Okay, so that's our root function, square root of x. If we have y equals the cubed root of x, can you take the cubed root of a negative number? Yeah, you can. The cubed root of a negative produces a negative. The cubed root of a positive produces a... So therefore, you're going to get this kind of shape. What if I have the fourth root of x? Is that going to look more like the square root of x or the cubed root of x? Square root of x, yep. It's going to be a little bit flatter. You notice I don't really draw it any differently. It's really tough to tell the difference. You just kind of want to get the general shape. And then how about the fifth root? Which one is that going to look like? Yeah, it's going to look like a cube root. I'm going to try to do a better job of drawing that one. So let's talk about other root functions, and then we'll move on to kind of our goal for the day, which is to transform functions that are parent functions. What about y is equal to x to the 2/3? This is where you're going to have to lean in here, folks. Y equals x to the 2/3, okay? Is 2/3 bigger than 1 or less than 1? Less than 1, just like y is equal to x to the 1/2. So it's going to have more of a shape like that. But let's think about the negative values, okay? This is the same thing as y is equal to the cubed root of x squared. If you were to plug in positive 1, 1 squared is, and the cubed root of 1 is 1. So you plug in a positive, it produces a positive. Let's plug in a negative. Negative 1 squared, 1 cubed root. Oh, so negative values also produce positive values, don't they? So it turns out this one looks like this. I call it the bird function because that's how I draw a bird. This is how I draw a person with a super long neck and no torso. And this is how I draw a bird. It's flying by. The bird function. You got a better name for it? All right. Let's look at a different one. Y is equal to x to the 3/2. Let's see what happens there. Is 3/2 bigger than 1 or less than 1? So it's going to head off like a parabola. But we have to think about what's actually happening here with our values. Suppose we plug in a positive 1. What's 1 cubed? 1. What's the square root of 1? 1. So a positive produces a positive. Now try a negative. What's negative 1 cubed? What's the square root of negative 1? Ooh, so you can't plug in any negative values, can you? And so therefore, this graph will look like this. Doesn't have any negative values. Reciprocal functions. Y equals 1 over x. It's called a reciprocal because x is dumped down into the denominator. A for the day. Who can tell me what x cannot be in this situation? Y. Can't divide by 0. So therefore, we have what we call a vertical asymptote at x equals 0. Asymptote. Now, some of you are listening, maybe making fun of me because I'm saying asymptote. I took 4 semesters of Greek. It's pronounced asymptote. Over the years, people also started to pronounce it as asymptote. You can pronounce it either way. Either way is correct. I choose to say asymptote because if I say asymptote, it puts the emphasis on but. And you'd be like, Mr. Guinness, why are you talking about but all the time? So I don't say asymptote. Got it? I'm sorry. That was inadvertent. Would you rather I pronounce it asymptote then? How about this? We're going to come up with a new name. Ashwitote. Okay? There we go. So, what do you produce these reciprocal functions, make sure you draw your asymptotes first. Okay. Now, there's one value you can't get out for y. Okay. Now, this is challenging. See if you can figure this out. Suppose I wanted to get a y value of 2. Do you know what x would be? If I wanted a y value of 2, what would x have to be? A half. Suppose I wanted y to be 20. What would x have to be? 1 over 20. Suppose I wanted y to be 100. What would x be? 1 over 100. It's the reciprocal function. Get it? Suppose I wanted to produce 0. Could you plug something in for x that would produce 0? You couldn't. So therefore, you have a horizontal asymptote. Because it goes through y equals 0 because it can never be equal to 0. The asymptotes are what the graph approaches but never touches. And so a negative will produce a negative, so it's down here in the third quadrant, and a positive will produce a positive, so it's up here in the first quadrant. That's what a reciprocal function looks like, and you will see them a fair amount as we move forward. What if I change it to this? Y is equal to 1 over x squared. Can you anticipate how it will be similar to the previous one, but also different? Think about it, folks. You've already said it once. What happens when you square something? It becomes positive. So therefore, it will always be positive, which means it always sits above the x-axis. And that will also be true if it was y equals 1 over x cubed, or y is equal to 1 over x to the 4th. If it's an odd power, they'll be one above and one below. If it's an even power, they'll both be above. What do you think? Not too bad, huh? So we'll do some examples to actually show you. So you need to commit all these to memory. And you can do that because you're Shuba Shmat. And you do it in all your other classes anyway. I'm going to show you my favorite function of all time. Turn on my calculator. I'm going to go into here, and I'm going to clear all this stuff out because it doesn't matter anymore. Clear. And I'm going to type in sine of the reciprocal function, 1 divided by x. And I'm going to zoom standard, and this is my graph. Pretty cool, huh? You're like, well, Mr. Gins, we thought it was going to be more impressive than that. Well, looks like something interesting happens right there, right? I'm going to zoom in on that and see what's going on. Ooh. Almost looks like a heartbeat or something, huh? It's called the love function. Let's zoom in even more, see what's going on. It's kind of fun. I'm going to zoom in again. Josie said it. It is called the barcode function. It is called the barcode function. You can actually produce any barcode ever exist in the entire world through this function. In fact, this function will produce an infinite number of barcodes and an infinite number of barcodes that never reproduce themselves. Anybody work at a store where you scan stuff? Okay, I want you to do this. I want you to type this in your calculator, then bring it to work and see if you can scan it and see if it comes up with a dollar amount. You know what I mean? You know what I mean? If it came up with, $2, a big deal. But suppose it's like $1 billion. Like, holy cow. I found something really cool. You got to figure out how to have fun with math. I'm trying to teach you guys, okay? Barcode function, totally awesome. Flip it over. Here we go. We got to get through this page. We want to talk about vertical shifts. Suppose you had a function, g of x, and you had another function, f of x, and they were the same exact function, except g of x was f of x plus k. There was something added onto the end of it. The fact is that would change the shape, or it wouldn't change the shape, it would just change the location. It would produce a shift k units up. What if we have a minus k? What do you think is going to happen there? Shift k units down. Well, that's just awesome. Horizontal shifts, g of x would become f of x minus h, or g of x would become f of x plus h. What's different about the h compared to the k in its location? Notice how this one sits on the inside of the function, like within the parentheses. Probably the most important thing that you can learn over the course of the next 3 days is this. If it's on the inside, it affects it horizontally. If it's on the outside, it affects it vertically. Most important thing you can learn. Crucial. Did I say horizontally again? Okay. Outside vertical, inside horizontal. And it's opposite of what you think. So this is a shift h units to the right. A lot of people see the minus h and they're like, oh, that's going to go to the left because it's a minus h. F of x plus h is a shift h units left. How do I remember that one goes right, one goes left? Here's what I do. I think about what do I plug in to make this section right here 0. And I would plug in h. Well, h is positive, so it moves to the right. What would I plug in here? I'd plug in negative h, so it moves h units to the left. That's how I remember it, and it always works for me. Let's do these 4. These should be a piece of cake, upside down, something you've seen before. I draw the parent function. What is the parent function? What does the shape look like? Parabola. So you draw the parent function. Then I'm going to draw the function with the transformation. Is the minus 3 on the inside or outside? It's on the outside. So is it going to affect it vertically or horizontally? Vertically. So it's going to shift it 3 units down. What does the parent function look like for the next one? Yeah, that little thingy off to the side. That's like the most common name that people say. It's the thingy off to the side. Yep, there you go. Good job. Okay, what do we plug in to make 0 here? What do you plug in to make 0? 4. So it's going to move 4 units to the right. What's the parent function look like for the next one? This one also has a very technical name. Squiggly thing. Yep, that's the most common result. Squiggly thing. Or S shape or snake thing. Whatever you want. So I have x plus 3 quantity cubed minus 2. Is the 3 on the inside or outside? So that could be horizontal or vertical. Horizontal. What do you plug in to make 0? So move 3 units to the left. How about the plus 2 or the minus 2? Down 2. So I'm going to move back 3 and down 2. I'm going to have the same exact shape then. What do you think? What's the next shape look like? A V? What are the 2 transformations? Four to the right and 3 down. Good work. Any questions on those? Then we do our last section. What if we have g of x and we turn it into negative f of x? Is the negative on the outside or inside? So therefore, it will affect it vertically. Vertical flip. A vertical flip would be over the x-axis. What if we took g of x and we transformed it to f of negative x? Is it a negative on the inside or outside? Inside. So that will affect it horizontally. Now, there's no easy way to say this. I'm just going to help you guys through the best I possibly can, okay? This is always good. Vertical flip, everybody's like, yep, I know exactly what happens there. Horizontal flip doesn't always go so well. So I'm going to try to help you work through that horizontal piece. I'm actually going to use some descriptions that aren't mathematically sound, but I'm going to tell you what's going to help you out the rest of the way. Because I know what I have to prepare you for. I have to be able to teach you how to do this eventually. You're going to graph negative 3 sine of 2 pi over 3 minus 2x plus 1. You're going to produce a graph of that. And in fact, when I teach you how to do that second semester, the median score in the class is not going to be 90 any longer. Anybody want to guess where it's going to be? It's going to be 100. When we do that, half of you will ace the test. It will be your best test the entire year. That's what the previous years show. You'll learn how to do that super, super, super well. Okay, we can get a lot of kids to do that really well. We just want you to make sure you can focus on kind of getting that basis right now. So let's look at this negative on the outside. First of all, I've got a graph of the square root of x. Is it negative on the outside or is it on the inside? Outside, so that's going to affect it vertically. So it's going to flip down like so. Is everyone okay with that graph? And what if I were to change it? So a few years ago I brought this up and this seemed to be helpful for people. Now the negative is on the inside. So that's going to be a reflection over the y-axis, so it's going to go back like that. Let's take it one step further. What if I did negative root of negative x? Some people say negatives are going to cancel. They're not. This is a vertical flip and a horizontal flip. Yeah, we can definitely produce all four of those. That's how they would look. Okay, parent function for the next one. Parabola, right? Now, when you see the negative in front of the x, what do you think of? Negative in front of the x. Is that negative on the outside or inside? So you're thinking horizontal flip, right? I'm going to try to get that out of your brain. Really only think about the horizontal flip when you're thinking about square roots. And I'll show you why. The 3 minus x quantity squared, here's a better way to think about it. What would you plug in to make 0? 3. So move 3 units to the right. When you square this, is it going to end up being a positive x squared or a negative x squared? Positive x squared. So it's going to go up. See how easy that was to think about it? What would you plug in to make 0 and then square it out? When you have a polynomial, just think of it like that. Because I will tell you guys right now, you will never get that problem in your entire life. And here's why. Watch. I'll square this out. I'll take 3 minus x, and I'll multiply it by 3 minus x. Negative x times negative x, positive x squared. Negative 3x, that's negative 6x. Negative, or 3 times 3, that's 9. Well, doesn't that just factor to x minus 3 quantity squared? This is the same as this. Like, well, Mr. Gens, how can that be? The reason why they're the same is if you take 3 minus x, quantity squared, if you were to factor out a negative 1, you would get a positive x minus 3. But what happens when you square the negative 1? It just goes away. So you get x minus 3 squared. They're the same thing. The question is, which one is your book more likely to write? The one in the red or the one in the green? They're more likely to write the one in the red. So horizontal reflections don't hardly ever come up. In fact, when you guys get to the trigonometry stuff, we're going to get rid of all the horizontal reflections together. They just don't come up. People don't write them like that. So let's think of the easy way to do it. We know what this looks like. It's a cubic. The question is, what would you plug in to make 0? So it moves 1 to the right. What does the plus 4 do? Up 4. And then what does the negative out front do? That's a vertical flip. If you were to cube this out, it would be positive x cubed, but then you would apply the negative. So because it would be a negative x cubed, it would start up and finish down. What would you plug in to make 0 here? 5. So it moves to the right 5. What's the negative on the outside going to do? Vertical flip. Goes down. The only time that you really need to focus on, excuse me, the only time you really need to focus on the negative on the inside is this. That's where it's crucial. Okay? What do you plug in to make 0? 3. But if you think about this, the domain 3 minus x must be greater than or equal to 0. So negative x is greater than or equal to negative 3. So x is less than or equal to positive 3. If x is less than or equal to positive 3, do I draw the graph off to the right or off to the left? Draw it off to the left. And that matches with the negative in front of the x. Really, the only time you got to worry about that horizontal reflection is when you're coming up with the square roots. That's where they come up most often. Okay? Hey, good job. You have 15 minutes. You have a worksheet. You can honestly get the worksheet done in the 15 minutes. I kid you not. Here you go.